Okay, so let us now look at this extremely long looking exercise 12. So this one involves proposition 2116, which is actually the principle of recursive definition. If you recall, in the very beginning, while we were constructing the system of natural numbers, what we did first, we laid out the piano axioms, the first 5 piano axioms, and then we went through this proposition 2116, which actually allows us to define sequences recursively. We use recursive definition everywhere in mathematics. For example, in group theory, we use it to define integral powers of group elements. In number theory, we define sequences using this principle. For example, we define the Fibonacci sequence, and many other some things are defined using this principle. So at the time we stated this principle, we also saw a proof of it, but it was not rigorous because at that point we were not introduced to functions. Although we knew already what functions are, but from the point of view of this text, functions made their appearance much farther down the road. So now it's in this exercise, it's our job to make things rigorous and precise. So what we have to do is this. We are given a function whose domain looks like this, which is the Cartesian product of the set of natural numbers with itself, and range is the set of natural numbers. And a natural number C is given to us. Having given these two things, we have to prove that there exists a unique function. There exists, first of all, we have been asked to show that there exists a function from the natural numbers into the natural numbers such that its value at 0 is that natural number C which has been chosen beforehand, and its value at the successor of the natural number n, which we are denoting by this symbol. You recall our treatment of the natural numbers from piano axioms. This is the successor of n, which ultimately turns out to be equal to n plus 1. But when the numbers were introduced, since addition was not available, so we had to devise a new notation for successor. So at that natural number, the value of the function is f of n comma a of n. And this is true for every natural number. And then we have to furthermore show that this function is unique. That is, this function satisfying these properties, there is only one such function. So a hint is given, and we will proceed according to the hint. So in the hint, what we have to do, given any natural number n, capital N, we have to show that there exists a function an whose domain is this, the set of all natural numbers starting from 0 and ending at that capital N, and range is the set of natural numbers, which satisfies properties that look somewhat like this. Although here there is a further restriction. The value of this function at 0 still has to be C, and this property still has to be satisfied by an, which is just like what we require a to satisfy. But this is true for all natural numbers which are strictly less than that number n, for which we are finding this function. We will first go through this. We will prove the existence and uniqueness of every an, and then using these ans we will define this a, and we will then show that this a satisfies these properties, and then we will prove that this function a is unique in the sense that it's the only function satisfying these properties. Now this is the first part of the exercise, but there is a second part also. Let us go through the second part, and then we will see why we need a second part. For an additional challenge, prove this result without using any properties of the natural numbers other than the piano axioms directly. In particular, without using the ordering of the natural numbers and without appealing to proposition 2116. This is natural because We are proving to 116. How can we appeal to 116? Okay, so what has been said here is that we are not allowed to use any advanced properties of the natural number system. We are only allowed to use the piano axioms, and in particular we cannot use the ordering of the natural numbers. Why? You see, we have used proposition 2116 to define addition recursively. Then using addition we defined order. If you remember, we defined for two natural numbers a and b, we defined a to be greater than or equal to b when there exists a natural number c such that a is equal to b plus c. So that means indirectly the definition of order depends on the principle of recursive definition. So what we are doing here actually is not getting us anywhere. We are using order here, you see, n less than or equal to n. So the existence of this relation or the definition of this relation depends on 2116. Then in this solution, since we are using order, so it's a circular argument. We are using order to prove proposition 2116. Then using proposition 2116 we are defining addition, and then using it we are defining order. So actually, although it looks a nice way of proving proposition 2116, but we are not achieving that here. We achieve that in the second part, where we are not allowed to use anything. You see, first the piano axioms come, then the proposition 2116 comes, and then after that only addition, multiplication, order, these things are being defined with the help of proposition 2116. So the proof of proposition 2116 should depend only on the piano axioms, nothing else, and that's why we will not be permitted to use this set whose definition depends on the ordering of the natural numbers. A way around this is given in this hint for the second part. In the second part, what we have to do, first show inductively using only the piano axioms and basic set theory that for every natural number n, you see here also we did something for every natural number n. We defined such functions, and we showed that such functions existed, and then we proved the other things. Here we have to prove that for every such n, there exists a unique pair of subsets of n, an and bn, which satisfy these following properties. An and bn should be disjoint. Their union should be the set of natural numbers. 0 must belong to n. The successor of capital N has to belong to bn. For every element in Bn, that is for every natural number in Bn, its successor n plus plus should also belong to Bn. And for every natural number in An which is not equal to n, the successor of that natural number should belong to An. Now once these sets are obtained, we have to replace this set in the previous solution by An and then proceed. Exactly like what we will do here. Only difference is that we will not be using this set, and instead of that we will use An. And in constructing An, and actually we are not constructing, but we are just showing that such An exists. In this, there is no mention of this greater than or less than. So we are not using any addition or multiplication. We are using nothing. We are just using piano axioms and some axioms of set theory, that's all. So let us see how the solution can be written. The solution in itself is not very difficult, but there are some fine points and there is high chance of making mistakes, so I have to be extra careful. Okay, but before we actually write the solution, let us just see what these sets will be ultimately according to these properties. You see, if you think of we are getting way ahead of ourselves. This is the numbered line. Since we don't yet know what real numbers are, so we should not be using this, but still you understand what I am doing here. This is the natural number 0. They have told us that for every natural number n, there exists a unique pair of sets an and bn. Their intersection, you see, if I assume an to be the set of all natural numbers lying between 0 and n, and the rest is bn, do I get these properties? Bn starts from the successor of n. Okay, so that is the first element of bn, if I say so. If we say first element, second element, etc. an and bn are clearly disjoint, and their union is the entire set of natural numbers starting from 0 and containing everything. 0 belongs to an, yes. N plus plus belongs to bn, okay. Whenever I have an n in bn, its successor also is in bn, because it will be further towards the right hand side. Whenever I have n in an which is not equal to this capital N, then its successor is also in an, and that is the property f. We are leaving n out because the successor of capital N is not in an, it is in bn. So you can see that the reason for using an in place of this, because they are the same thing. Although we can't prove that they are the same thing before developing the theory of order. Okay. Anyway, so this is the second part. So we now look at the solution and we start with the first part. Okay. We apply induction on n to prove that for any n belonging to the set of natural numbers, there exists a unique function with this domain and this range such that the value of it at 0 is c, and this is equal to this for every n in n such that n is strictly less than n. We will prove this by induction on capital N. So the first value of n will be n equal to 0. So for n equal to 0, consider the function A0 defined from this set into n. If n is 0, you can see that this set will consist of only 0. So that means we need to define this function at 0 only. Looking at the properties, it's natural to define it at 0 to be equal to c. Okay, so this function is just, it has only one element in its domain, and at that element its value is c. Clearly, A0 of 0 is equal to c, because that's the definition. So the first property is automatically true from the definition, and if n is a natural number such that n is less than n, in our case this is equal to 0, then a0 of n plus plus is equal to f of n comma a0 of n. There is no doubt about this one, but what about this statement? If n is a natural number that is less than 0, then such a statement is this true? It is true. It is vacuously true, because you see, it's a statement that's an implication, and the implication looks like this: n belongs to n and n is less than 0 implies this. In this implication, the hypothesis is false. So the implication is true, it is vacuously true. Hypothesis is false because no natural number is less than 0. Every natural number is greater than or equal to 0. So that's why, nevertheless, although it's vacuously true, it's true. This statement is vacuously true. So you can see that we have actually found out a function for which these properties are true. Now we prove uniqueness of the function. We actually don't have to prove, but it is self-evident. Also, clearly a0 is unique. There can be no other function like a0. Why? Because the domain is supposed to be this set only, and at that point the value has to be c. There is no other way, because this has to be satisfied. So a0 is the only possible function. Any other function, if you think of, if that is different from a0, it has to have some other value at 0 than c, but then that function would not satisfy this. So the only function satisfying these properties is a0. So for n equal to 0, we have actually got what we want. Thus, claim is true for n equal to 0. This is the basis for our induction. Okay, now we make the induction hypothesis. Now assume that the claim is true for some natural number n, that is there exists a unique function an such that an at 0 is C and an at the successor of n is equal to this. Okay, so this is our induction hypothesis, that such a unique function exists for this capital N. We now have to prove that such a function exists for the successor of n, that is n plus plus. This we have to prove, and this function we are now going to define. Okay, now consider the function an plus plus and its domain is the set of all natural numbers less than or equal to n plus plus. Keep in mind that n plus plus is nothing but the next number to the right of n, that is the successor of n. By there should be a formula an plus plus at the natural number n is defined to be equal to an of n if n is less than or equal to n. If n is less than or equal to n, then n is in the domain of an itself, so we can define the value of this new function at that point to be the value of the old function itself. However, if n is equal to n plus plus, then we define the value to be this: f of n comma an of n. Does it make sense? It makes sense because you see capital N is still in the domain of an, so this value an of n makes sense, and that is a natural number. N itself is also a natural number, and our original function f has domain the Cartesian product n cross n, so this value makes sense, it's a natural number. Okay, now the question is, are these conditions true for this new function? That we have to verify first of all. Okay, note that. Now I think I need ink. Give me a moment. Note that what happens if we try to calculate this. 0 of course is less than or equal to capital N, because capital N is a natural number. So that means according to this definition, this is equal to an of 0, and we already have an of 0 to be equal to c. So the value of an plus plus at 0 is c. So this is what we want. Okay, so this part is over. Now let n be a natural number such that n is strictly less than n plus plus. So we now want to know if n is a natural number that is less than n plus plus, whether such a statement or such an equation is true for this new function. Okay. Now the cases will come. If n plus plus is less than n, is it less than n or less than or equal to n? Let me see. Okay, otherwise I will make a huge mistake. Okay, so I am allowed to take less than or equal to n. It's difficult to keep track of these things and memorize everything. Memorization is actually not the aim. If n plus plus is less than or equal to n, then understanding the thing is the main aim. An plus plus n plus plus is equal to, so if n plus plus is less than or equal to n, then n plus plus belongs to the domain of the previous function. So according to this definition, this will be equal to n plus plus. So we are allowed to use this formula here. This is equal to f of n comma n. Now n plus plus is less than or equal to n, then n is also less than or equal to n, because n is less than n plus plus. We already know these things from our properties of natural numbers and the order relation. So n also belongs to this domain of the previous function. So that means this is equal to this. So we can write, let me write it in the next line, fn an plus plus n. So you can see that we actually have the same or similar equation just like this one, where capital N is replaced by n plus plus, and this is when the this condition is satisfied, that is if n plus plus is less than or equal to n. Okay. If okay, so so there, when will this happen? That's what I am thinking. See, what is the largest value of small n possible? The largest value that small n can take is capital N, because after that we have n plus plus. So if this is taken, then n plus plus of course is equal to n plus plus, and this is not less than or equal to n, this is greater than n. So this is the only case that has not been accounted for in this part of the calculation. So we now have to look for this case. I mean, what happens in this case when n is equal to capital N? If n is equal to capital N, then what happens? Then what happens to this? Okay, now again let's look at the definition. Now n is equal to n plus plus, so this part of the formula has to be used. So this will be equal to Fn An n. Is it okay? Yes, because at that point this is the fixed value. Okay, now we have small n is equal to capital N, so in place of capital N we can write small n. Here also in place of capital N we would write small n, and because capital N belongs to the domain of the previous function, so we actually can write an plus plus. I hope you understand. I could have written another step, but I mean keeping these n's capital and then make them small, but I am writing it here itself. So you see that this formula an plus plus n plus plus equal to this is true in all the cases. So that's what we wanted. So the two relationships that we want the function to satisfy, they are being satisfied. Okay. So such a function an plus plus exists, but we are not over yet. We have to now show that this an plus plus is unique. Okay, so and for that we will assume that there is some other function and we will arrive at a contradiction. Suppose there exists a function b which looks just like this one. Just like this one means not using the formula but in terms of properties. Such that b of 0 is c and b of n plus plus is equal to f of n comma b of n for all n belonging to n and okay, our supposition is not over, and b is not equal to an plus plus. Okay. It's straightforward to show that that the restriction function, okay, now the domain of B is exactly the same as the domain of AN++. Now if we remove this last point from the domain and concentrate our attention on the subset, resulting subset, then we are restricting B to that subset, restriction of functions. So the restriction function, and let us call it by the symbol D. This is the restriction of B to this subset. N is less than or equal to N, that is, we are removing the successor N++ from this domain. This restriction function satisfies the following properties. D of 0 is equal to C and D of N++ is equal to this for all n belonging to N, such that N is less than N. One can verify this. In fact, these properties come directly from these properties. The only thing is that you see B of 0 and D of 0 are actually the same thing. It's because 0 belongs to this domain and 0 also belongs to this domain, and D is nothing but the restriction of B. So the formula for D has not changed, only the domain has shrunk, okay, by 1 point. So D of 0 is